As promised, our next video will talk about the energy of membrane transport. And so our goals in this video are to review the concepts of free energy associated with concentration gradients. If you remember the term concentration cell when we did electrochemistry, we're going to be using those ideas. And then we want to apply those to this membrane transport idea. So we have two big ideas. We have this idea of free energy, and we had an equation, so we had our free energy equation, delta G, and we have our fluid mosaic model for the lipid membranes and membrane transport. And so we want to marry these two big ideas and eventually be able to quantitatively understand the energy associated with membrane transport. So let's look a little bit. We earlier looked at this equation in the concept of chemical change. So if I had this chemical reaction, I could determine my reaction quotient, which at its simplest is products over reactants. Remember that was Q. It's the exact same equation as for K, the equilibrium constant, but we can calculate Q at any mix. It doesn't have to be at equilibrium. So it's each product raised to its coefficient over each reactant raised to its coefficient. And we know that the Gibbs free energy at any given point is equal to the standard Gibbs free energy. That's when 100% of the reactants go to 100% products, plus this factor, right? RT natural log of, and this is Q. So we have that equation. I'm going to add just a little bit right here. We're going to add that little prime symbol because remember that when we're talking about standard, it usually means 1 molar concentration. But in biochem, we're going to talk about pH of 7. So our H plus can't be at 1 molar concentration. So that's that little extra piece. Now we have looked at this two ways. We talked about having reactants and products and looking at that energy hill they had to go over. In this graph, where we're looking at this reaction progress, we're really thinking about one molecule and the pathway of one individual molecule moving from reactants over here to products. And each molecule has to go through that high energy transition state. The other way we have thought about it, same reaction, so my reactants, my products would be at the same level. But now we're thinking about the reaction mixture. And so at every point, we're not thinking about any one molecule, but we're thinking about those infinitesimal changes in the reaction mixture. And so we see something like this. And we hit this minimum right here, which is where we're at equilibrium. And at that point, we know that's the point where delta G, not standard Gibbs free energy change, but delta G equals 0. Remember, our standard Gibbs free energy change was all reactants to all products. All right, so this is kind of a review, and we're really going to be thinking about this reaction mixture side of it over here. So remember, if we're over here, we're still proceeding forward, so delta G would be negative. It's still spontaneous to go forward. But if we're over here on the other side, we've overshot our equilibrium. Delta G would be positive. It's no longer spontaneous to go forward. We need to go back to get to equilibrium. All right, so doing a little math, we know that at equilibrium, delta G is 0 and Q is K, and so we have this equation. That natural log, not lim. And now what we want to do is we want to apply this to diffusion. We talked really about chemical change. We want to talk about diffusion, which is more of a physical change thing now. So think about glucose transport in or out of cells, so into or out of a cell. So we could have glucose going this way, We could have glucose going that way. Which way is spontaneous will depend on the concentration gradient, because remember it's spontaneous if we're moving in the direction of lower concentration. The molecule is the same. It's glucose in solution if it's on the inside of the cell. It's glucose in solution if it's on the outside of the cell. So if you remember, we used Hess's law back here in Gen Chem to calculate the standard Gibbs free energy change. So it was the free energy change of the products minus the free energy change of the reactants. And you could go to those tables and look it up. Well, now our products and reactants are the exact same thing. So the standard Gibbs free energy change will be 0. So if we come back up here and plug in 0 for the standard Gibbs free energy change, we'll find the change in free energy is RT natural log of Q. Now you want to be careful. Don't get confused. For a chemical reaction, we found the standard Gibbs free energy was negative RT natural log of K. But for diffusion, where we have the same starting and ending molecule, here is the equation that we're really going to be looking at. This delta G equals RT natural log of that reaction quotient. So this bottom one is going to allow us to calculate the energy of a molecular ion passing across a membrane. All right, let's look at how we could use this. So if we have this membrane, so notice we've got a membrane across the middle, we have a higher concentration up top and a lower concentration on bottom. So we know that we would have, we expect spontaneous movement of those molecules moving through. We know RT natural log and Q, remember, is our reaction quotient. So Q would be the final concentration over the initial concentration. Okay, we had A2 over A1 here, but you could do final, initial. And we're going to say, okay, we expect this, right? We expect this to move from top to bottom. And so I am going to talk about this being my final this being my initial. And if I plug these in, right, I could plug in and say RT natural log. And if I look at that, my final, this is a lower concentration. I have my smaller number up top over my larger number on bottom. This is going to give me a negative value, which tells us that it would indeed be spontaneous. Delta G would be negative when I plug these in. And initial and final may be a little confusing, but think about for each molecule. It's starting up here, so it's part of this solution, so that's its initial concentration. And for that individual molecule, it's moving down here, so at the end, it's down here, and it's part of that concentration. All right, let's look at an actual calculation we could do. So we want to calculate the free energy for the process in which glucose diffuses across cell membrane from an external concentration of 0.5 millimolar, right, to an internal concentration of 0.09 millimolar. And we're talking about glucose diffusing in this way. So if I write my equation, I know delta G equals RT natural log of Q. I know delta G equals R, so 8.315 joules per mole Kelvin. We often use 8.314, whichever is fine, times 310, because we need our absolute temperature, times the natural log. Now it's going from the higher to the lower concentration. So it's products over reactants, or it's final over initial, so 0.09 over 0.5. And when I work this out, I got negative 4.4 kilojoules per mole. So yes, this would be a spontaneous process. We would expect that glucose to spontaneously move into that cell. So let's look at another example. So is potassium transport spontaneous for this uniport? So we see the potassium's moving into the cell. We see that the outer concentration is 4 millimolar and the inner concentration is 140 millimolar. So starting off, I'm going to say, wow, it's moving from low concentration to high concentration. No, I do not expect that to happen. But then I'm going to stop and I'm going to say, oh, wait a minute. I've got some more information. There is a membrane potential. And when I look at this membrane potential tells me that there is a differential in charge on the two sides of the membrane. And we see we've got a positive charge on the outside and negative charge on the inside. Thinking about that membrane potential, would you expect this potassium to be attracted to a negative charge? Yes, absolutely. So now I've got a problem. My concentration tells me that this is not going to be spontaneous. But that membrane potential tells me that, wow, yes, the potassium would want to move in there. And so I need to figure out essentially which of these two wins. One's favorable, one's not favorable. And we know how to calculate the delta G for the concentration, but we need to know how to calculate it for the membrane potential. So let's review that idea. So membrane potential is measured in units of voltage. If you think back to our electrochemical cell, there was a relationship between the standard Gibbs free energy and the voltage and charge that passes that voltage. And we had this relationship right here. And we said that we could look up on the standard reduction table, right? If we wanted to know the standard cell potential, well, we'd look up the electron acceptor, electron donor. Remember the standard reduction potential of the thing being reduced minus the thing being oxidized, and we could calculate that. N was our moles of electrons. F was Faraday's constant. Which was coulombs per mole of electrons. All right, so N times F gave us coulombs, unit of charge. Okay. And when you work this out, this gave us coulombs, this was in volts, and 1 coulomb volt is 1 joule. So we get these energy units. So the change in the free energy turns out is equal to the electrical work that can be done by a cell. It quantifies the amount of charge kind of moving across that voltage. If you remember back in electrochemistry, we talked about voltaic versus electrolytic cells. Voltaic were spontaneous, things like batteries. They had a negative delta G, which means they had a positive cell voltage. when we talked about electrolytic cells, now they have a positive delta G, a negative cell voltage, and we had to push the electrons. We had to add some energy to get those electrons to go where we wanted to. So let's apply this to our cell. Most cells have more anions than cations inside the cell compared to outside. So if we're looking inside the cell, we'll have more negative charge down here, more positive charge outside the cell. This separation of charge causes a voltage across the membrane space. And we're going to use this delta psi to indicate that, okay? It's analogous to E. We used E for the cell potential when we talked about it in electrochemistry. So we can calculate delta psi using a form of the Nernst equation. So if you remember, we already looked at this equation. And then we said, hey, delta G is the same as negative NF times the cell potential. So we plug that in both places, and we ended up with the Nernst equation. Now, I'm not going to ask you to calculate these in this class. I will give you the cell potentials, but I just want you to see where that comes from because you might need to do it in other classes. We are going to end up using this equation that says that delta G equals Z times the Faraday's constant times delta psi. When you look at this, we're using Z instead of N. That's what we used in electrochem. So in electrochemistry, we had just electrons moving, but now Z is going to talk about the quantity of charged species because they're not all just electrons. Quantity of charged species. F is still the Faraday's constant, and here's our membrane potential. So if we drop back down to our question, let's see if we can just figure it out qualitatively first. Looking at this and thinking about the overall total, that's that T, delta G. It's going to be the concentration part and the potential part. Looking at the concentration part, I know C2, it's moving in, so C2 over C1 would be 140 over 4. I'm going to get a positive value over here. That's what I predicted. It is not going to be spontaneous based on just the concentration. Now, if I come over here and I look at this, I know, whoops, that's not what I wanted. I know that this is a negative value. Okay, it's actually negative 0.05. So this overall thing is going to give me a negative value, and it will be favorable based on the cell potential. Also what we expected. Okay, notice that our charge here was +1. If we were trying to move electrons, now negative times negative gives us positive. It wouldn't be favorable. So we are going to have to actually do the math to figure out if this would be spontaneous or not. So when I look at this, 8.315 joules per mole Kelvin times my 310 Kelvin times the natural log of 140 over 4 is that part on the left. And then for the part on the right, I've got my +1 charge because it's potassium ion times my 96,500 coulombs per mole times negative 0.05 volts. Remember that 1 coulomb volt is 1 joule, and if you work all the way through this, you are going to come out, and I converted it to kilojoules, to 4.3 kilojoules per mole positive. Okay, so it is non-spontaneous. All right, that is the basics of how we are calculating those. We will come back and look at even more energy of cell membrane transport in the next video.